Hello and welcome to Lab 5, the Human Rocket, where I'm going to discuss Felix's attempt to break the sound barrier. The main objectives of this lab is to get the necessary data for the model, make a model using VPython, compute the energies, compare the real jump graph with a predicted jump graph, plot in the graph window the energy changes that I computed in the model. And here are some of the system's properties. We assume that the system consists of Felix and his suit only. The mass of the system is 118 kilograms. The initial position, which is in the y component only, is 39,068 meters. The initial velocity is 0 because he's still at rest. The forces acting on the system are the gravitational force, which is Fg equals minus m times the acceleration due to gravity times I hat, which is the positive y component, and the drag force, which is the drag coefficient times the area times the velocity squared times the density of the air divided by 2. And here are the physics principles that I used. The first one is the momentum principle with Newton's second law, which is Bf equals Pi plus Fnet times delta t. And from it we can find the final velocity and the final displacement. And I also use the energy principle, but here the system consists of Felix, his suit, and the Earth. And of course, delta E equals 0, and delta E equals delta K and plus delta UG. And here are the equations for the kinetic energy and the gravitational potential energy. Here are the constants that I use in my calculations. The first one here is the radius of the Earth from New Mexico City, which is where Felix jumped, and the mass of the Earth, and the universal gravitational constant, big G. Now, the forces. The first one is the gravitational force, and from this equation over here we can find the acceleration due to gravity, and that's because it differs depending on the height, and R here is the radius of the Earth plus the height of the system. And as you can see here, at the initial position, the acceleration is 9.688 meters per second squared, and this is not the same as 9.8. So for accurate calculations, we used this equation over here to find the acceleration. And then we can apply it here to find the force, the gravitational force acting on the system. Next, the drag force. We can determine the drag force with this equation over here. The coefficient for normal skydivers is 1.2 to 1.3. So with the pressure suits, we assume that it's 1.4. The surface area for a normal skydiver is 0.75 meters squared. So we assumed with the pressure suit that it's 1 meter squared. And we can determine the velocity from the loop. So the only thing left is the density of the air, and we combine it with this equation over here, which is P, which is the pressure divided by 0.2869 times the temperature in Celsius plus 273.1, and we can find the temperature in Celsius and the pressure with these equations over here, and this is only valid in the upper stratosphere, which is 25,000 meters and higher. I get these equations from NASA's website. I have already put the necessary information in the code, so there's no need to review them here. So let's run it. As you can see here, the drag force increases as it increases its speed, and it's almost approached terminal speed over here because the drag force and the gravitational force have the same magnitude but opposite in direction. And here's the predicted speed graph that I made, you can see that he first speeds up, but when the drag force becomes greater than the gravitational force, he accelerates upward, decreasing the speed. And here's the observed speed. You can see that it has the same shape, but the maximum speed here is higher, and that's because the drag force in my prediction was higher than the real drag force, and that's because I estimated the, the drag coefficient and the surface area of contact. And here's Felix's speed versus the speed of sound, but based on height, not on time. So as you can see here that he breaks the sound barrier at almost the height of 30,000 meters. The maximum speed was 315.92 meters per second, and the time that it took him to get to this speed was 45 seconds, and it happened at the height of 30,275.93 meters, and the speed of sound at that height is 301.7 meters per second. So he broke the sound barrier and became faster than the speed of sound at that height. Assuming that the kinetic energy and the gravitational potential energy are the only energies affecting it, you can see that the total change in energy is not zero. And that's because some of the energy got dissipated and transferred into thermal energy. And here's the updated equation as you see here. And here's the energy graph. Based on the updated equation, you can see that when the kinetic energy increases, the gravitational potential energy decreases, and the change in thermal energy also increases when the change in gravitational energy decreases. What effect does a change in the density of air with altitude have on your predictions? Rho here is the density of the air, and if the density increases, then the drag force would increase and the velocity would decrease because the drag force is in the opposite direction of the velocity. What effect does a change in temperature with altitude have on your predictions? If we get higher, the temperature would increase based on this equation. And if the temperature increased, then the density would decrease, which decreases the drag. And also not just the density would decrease, but also the pressure, which in turn decreases the density even more. What would happen if Felix were a fraction meters per second with only 19 seconds? Conclusion.